Hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics, and I'm Aman, welcoming you all to a new amazing video in which we are just moving further in Basel's function. And if you have I have uploaded one of videos on this topic earlier. Actually, I think I have uploaded this yesterday, right? I think you have to watch that video to begin here because we are just going to continue from there itself. And actually, this should be the first video on Bessel function because we are going to derive the Bessel function, that is j sub n of x, that was the infinite sum as r goes from 0 to infinity of negative 1 to the r over r factorial times n plus r factorial and times x over 2 to the n plus 2r. Or you can write this as the infinite sum as r goes from 0 to infinity of negative 1 to the r over r factorial and gamma of n plus r plus 1 times x over 2 n plus 2r, right? And yeah, we are going to derive this from this thing that is known as Bessel's differential equation. And the disclaimer for this video, this video is, guys, this is going to be a quite long video as we are going to derive this, so you have to be patient to learn something from this video. So the Bessel's differential equation is x squared times y double derivative plus x times y first derivative and plus x squared minus n squared times y equals 0. And basically what it is, this is x squared times d2y over dx squared plus x times dy over dx and plus x squared minus n squared y equals 0. So from here we are going to derive our target infinite sum, that is known as Bessel's function, this one. So yeah, this is going to be quite long video, I think, because yeah, we have to do a lot of things, and I think we should begin from here because if we waste our time, we are not going to do that. Okay, so first things first, we are going to assume that our y equals, oh, I'm sorry, yeah, y equals, oh, let me just change the pen. Yep, it's good. So y equals the sum as r goes from, oh, I think it's out of the required zone, maybe. Yep. So this is the infinite sum as r goes from 0 to infinity of a sub r x to the r plus s. So this is what we are going to play with after assuming y. And next, let's find the first derivative of this function. So taking the derivative with respect to x on both sides, so that's gonna give us, well, since the summation and the AR is a constant with respect to x, so and the derivative of this thing is just r plus s times x to the r plus s minus 1. And if we go further for the second derivative of this function, so that's gonna give us the infinite sum as r goes from 0 to infinity of a sub r, r plus s, r plus s minus 1, x to the r plus s minus 2. Okay, so now we are having our dy by dx and d2y by dx squared. Actually, I'm sorry about this. Yep. So let's just plugging these two things in here itself, right? From here and here, let's just plug them. And well, remember, we have to just go through this one also. Let me just, yeah, we have to go through x squared times y, and y was this one, and and similarly for n squared times y. So yeah, we can do that here itself. So if we play this with if we continue here, so that's gonna become x squared times the d2y by dx squared is the infinite sum as r goes from 0 to infinity of a sub r plus s, r plus s minus 1, x to the r plus s minus 2, right? And then plus x times the first derivative, that is infinite sum and a sub r of times r plus s, x to the r plus s minus 1. And actually I'm having slightly less pages, or maybe just I have to shift this here to have some space. And yeah, oh, I'm really sorry guys if you're having some sort of trouble like in background music, because there are some illiterate people who are just making noise, and I can't do anything. I'm really sorry for that. Just please bear with me. And if we talk about x squared times y, so this is what we are having: a sub r x to the r plus s and minus n squared. That's gonna give us r equals to 0 to infinity of a sub r x to the r plus x equals. So yeah, this is the big stuff that we are having after we assume that we are going to play with y equals that infinite sum. And if we plug the derivative, the first derivative and the second derivative of that y, so after plugging all the stuffs, we are left with this big chunk of things. And now we're just going to move ahead with this only. And what the next step is, we are just going to let me change the color maybe. Yeah, we are going to multiply this one to here and this one to here. So you're gonna have a very fascinating result. It's not very fascinating, but yeah, it's quite good, because that's gonna give us x to the r plus s, and similarly here itself. So yeah, let's just do that here. So this becomes the infinite sum as r goes from 0 to infinity of a sub r, r plus s, r plus s minus 1, x to the r plus s, plus the again sum as r goes from 0 to infinity of a sub r, r plus s, x to the r plus s. And then if we talk about negative n squared, so that's gonna give us r from 0 to infinity of a sub r x to the r plus s. Well, why did I write n squared, like the coefficient of, sorry, why did I write this term first? Because we are having something common in all of this, and this is what it's common. So yeah, now we are just going to play here with these three things. So, and the last term is not common like these things. So that is something like this one, as r goes from 0 to infinity of a sub r x to the r plus s plus 2. You can see this right from here when you multiply this to this. So yeah, you are going to just have that result only. Okay, and now if we go further, so we're just going to take common in these stuffs. And before that, let me talk about something here. If we talk about r plus s times r plus s minus 1 plus r plus s, so what we are going to have is, let's just multiply these two things. So that's going to give us r squared plus rs minus r plus rs plus s squared and minus s. And on, and in this parenthesis we are having s r plus s. So you can see we are having a nice cancellation over here, because this r cancels out this r, and this, where's the s? Oh, yeah, this s cancels out with this s. So we are having r squared plus 2rs plus s squared, and that is equals to r plus s whole squared. How cool is that? So yeah, we are just going to use that stuff only. Let me just erase this for a bit. Or should I erase this down, or should I just uh, sort in the length of this thing? I think I don't want to erase this down. Oh, I'm sorry. Wait a second. Uh, okay, let's just I think okay, okay, okay. Yeah, it's good. It's good. Okay. So yeah, let's just use the all three terms in written in green color. So we are going to take common the infinite sum as r goes from 0 to infinity, and we can take a sub r common as well, and then this where parenthesis. So it's r plus s times r plus s minus 1 and plus r plus s, and whole to the common out r x to the r plus s, and we are left with, oh, I'm sorry, this was equal to 0. So r equals 0 to infinity of a sub r x to the r plus s plus 2 equals 0. Okay, and why did I hope you just got this, why I just explained you what we got after solving this stuff. So yeah, let's just plug that down here. So we are going to have the infinite sum as r goes from 0 to infinity of a sub r, and this r plus s whole squared. Oh, I'm sorry. I'm really, really sorry, guys. Let me just fix it what I have just did. Oh, I'm sorry. Uh, 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 uh. I just left something here that I shouldn't mean to left. Okay, yeah. So I left the n squared. I'm sorry. Oh, okay. So it's n squared and times x to the r plus s. And this sum, as it is, r goes from 0 to infinity of a sub r x to the r plus s plus 2 equals 0. Okay, okay. And in this second infinite sum, we are just going to change the index variable as r changes to r minus 2. So the second infinite sum becomes the infinite, sorry. Okay, well, for the sake of not getting confused, let's just uh, write down only summation instead of just putting their limits, because in the end we are just going to have from 0 to infinity, but we are going to have a lot of things. So for the sake of not confusion, let's just not write the limits. Please don't hate me, guys. Okay, so let's say r tends to r minus 2, so this becomes a sub r minus 2 x to the r plus s. And now we can do the thing that we have did with the first three terms as well with the fourth term. So we are having um, uh, summation of a sub r and r plus s whole squared minus n squared times x to the r plus s plus this one that we have just changed the index variable. So a sub r minus 2 x to the r plus s. And now we can successfully take common the x to the r plus s and the summation as well as common. So this is equal to 0. So the summation of let me just put a parenthesis here, a sub r of r plus s whole squared minus n squared and plus a sub r minus 2. Oh, I'm sorry. I mean to just place it slightly below here, and yeah, it's good. And whole times x to the r plus s equals 0. Okay, that's good. If this equals 0, so basically this thing is also equals 0, right? We can just do that. It's not a challenge here, right? Okay, so yeah, let's just do that here. So r a sub r of r plus s whole squared minus n squared plus a sub r minus 2 is also equals to 0. And keep in mind that n should be greater than or equal to 2 to, oh, I'm sorry, it's not n, actually it's r. Oh, I'm sorry, yeah, it's r, because r, the infinite sums begins from 0 itself. So we are not talking about the less than 0 terms. And if we are having some sort of less than 0 terms, so that is basically 0, because yeah, you can just do that. So this basically becomes, if you calculate for a sub r, so that's going to give us negative of a sub r minus 2 over r plus s whole squared minus n squared. And here, if we calculate for s, how are we going to do that? Let's calculate for s. How are we going to do that? While plugging r equals 0. Okay. Or let me just pack it in a box. Okay. So for s, so let's just plug r equals 0. So it's a naught minus a sub minus 2 over um, this is s whole squared minus r squared, since r is 0. And as I told you, we are talking about greater than 0, right? So we don't talk about uh, less than 0. So if you are having a sub minus 2 or a sub minus 3 or anything less than 0, so that is always 0 for our case. So it means that this thing is 0. So a sub a naught s squared minus n squared equals 0, and that basically says s equals plus minus n. Okay, so yeah, we got a value for s, and now we are going to play this with after plugging s equals positive n. So for s equals n. Okay, so when you plug s equals n in a sub r, so that's gonna give us a sub r minus 2 over that's r plus n whole squared minus n squared. And when you calculate this after expanding the r plus n whole squared term, so you are going to have negative of a sub r minus 2 over r times r plus 2n. Yep. And yeah, this is what we are going to play with further. So I just want to write this down here, minus of a sub r minus 2 over r times r plus 2n. Okay, and this is cool, isn't it? Oh, I'm sorry. Okay, so yeah, and now, since, let me just write this down here for the sake of, yeah, since a sub r relates with a sub r minus 2, the old terms, like coefficients actually, vanishes, right? So that basically means we are going to let r equals 2k, because we are having only even terms. So let's do that here. So when you plug r equals 2k, so that's gonna give us a sub 2k equals minus of a sub 2 k minus 1 over 2k times, that was 2k plus 2n. Yep. Okay. Okay. Let's simplify this further. Let's just use recurrence formula to simplify this. Oh, well, before that, let's plug k equals 1. So a sub 2 comes out to be negative of a naught over 2 times 2 plus 2n, right? And when you plug k equals 2, so that's going to give us a fourth equals negative of a sub 2, right, over 4, or maybe you can, yeah, 4 times 4 plus 2n, right? Yeah. So, and when you plug this thing here, so you are going to have a sub 4 equals um, a naught over 2 times 2 plus n, 4 times 4 plus 2n. And yeah, this, when you talk about the generalization, the general term, so that keeps going up to, yeah, n plus 1 terms. Okay, let's just do this, right? Our first term is negative and the second term is positive. So it's something like negative 1 to the k, and a naught is common, so yeah, it's good. And then if we talk about the denominator part, so that is something like this one. So it's like 2k times 2k plus 2n times um it's 2k 2k minus 2 times 2k minus 2 plus 2n, and that just keeps going. So basically what we are having when you generalize this, so a sub 2k comes out to be negative 1 to the k times a naught over, that is 2k times 2k plus 2n, right? And times 2k minus 2, 2k minus 2 plus 2n, and that keeps going. Well, let's talk about a sub. Let's plug k equals 2 for the sake of proof that we have just talked here about a sub 4. Let's do this here itself. So when you plug k equals 2 here, so it becomes a to the a of a sub 4 negative 1 to the fourth a naught over it's 2 times 2, that is 4, and this is 4 plus 2 and I'm sorry guys, and this is when you plug, so this is 2 times 2 plus 2n, and yeah, that's it, because we don't need to go further, we just have two terms. If we talk about k equals um 3, yeah, if we talk about, so we are going to have three terms like this. We consider this one as first one term, or maybe you can talk about two terms. So for k equals 3, it's going to be 6 terms, right? So yeah, this is what this is what we had proved earlier. So yeah, this is what the generalization of a sub k, a sub 2k is does looks like, right? Okay, and now if we talk about, let's go further. So a sub 2k, negative 1 to the k times a naught over, when you take common 2 from all the stuffs. So since we have 2k terms, so if we take common 2, so we are going to have 2 to the 2k, and times you are going to have um, k times k plus 1 times k minus 1. Oh, I'm sorry, it's not k plus 1, it's k plus n, k plus n, k minus 1, and this is k plus n minus 1, this is k minus 2, and this keeps going. So yeah, k vanishes, so you are going to have in last, so you're going to have 3 times 2 times 1. So when you talk about this k minus 1, k minus 2, and 3 to 1, so that's becomes k factorial. Okay, and if we talk about this thing, so the last term would be n plus 1, something like that, because k is going to vanish, and this stops at n plus 1, right? Okay, so basically we are having a sub 2k equals negative 1 to the k times a naught over 2 to the 2k, k factorial. And if we talk about this thing, so let's write this as gamma of k plus n plus 1. And what did you notice something like how would I write this down? This is not going up to 1 because this ends up at n plus 1 only. So neutral, to neutralize that, I'm just going to multiply with gamma of n plus 1 and divide with gamma of n plus 1. Actually, I did that here itself, right? And when you do that, so oh, I'm sorry. Let's do this step by step instead of just jumping. So we are having k plus n k plus n minus 1 dot to n plus 1, and let's multiply with n factorial and divide with n factorial. Since n factorial is gamma of n plus 1, if you are not clear with this, you can just consider my introductory video on gamma function. I have uploaded this on my YouTube channel. So a sub 2k becomes negative 1 to the k times a naught times gamma of n plus 1, and this whole thing becomes gamma of k plus n plus 1, 2 to the 2k times k factorial and gamma of n plus k plus 1. How cool is that, guys? Like, believe me, like, yeah, this is really cool. Let me just write this down here one more time. So a sub 2k was minus 1 to the k a naught and gamma of n plus 1 over 2 to the 2k times k factorial gamma of n plus k plus 1. Okay, and now we are going to plug this in our sum. So where we had our sum, let me just figure this out. Okay, uh, where is that? Wait a second, wait a second. So yeah, let's just we had replaced like here. We had replaced r equals 2k. So that basically means what we had did here is y becomes k equals 0 to infinity of a sub 2k times x to the r plus it was, oh, I'm sorry, it's not r, n plus 2k, right? Yeah. So yeah, we are just going to plug a sub 2k that we have calculated here in our y. So y was the infinite sum as k goes from 0 to infinity of a sub 2k x to the it was n plus 2k, right? Okay. So when you plug this here, so you are going to have the infinite sum as k goes from 0 to infinity of negative 1 to the k a naught gamma of n plus 1 over 2 to the 2k times k factorial gamma of n plus k plus 1 and times x to the n plus 2k. Okay, and let's just write this down further one more time, this one. So y was our final, its second final result. Oh, I'm sorry, I just messed up with the index variable, but it's all right. So negative 1 to the k a naught, and that was gamma of n plus 1 over oh, I'm sorry, 2 to the 2k and times k factorial gamma of n plus k plus 1 and times x to the n plus 2k, right? So yeah, this is what we are having, and now we are just going to replace our a naught with 1 over 2 to the 1 over 2 to the n and times gamma of n plus 1. Since we can plug this here, we can do that. It's like, you know, this is the final result actually. But for the definition of the Bessel function, we have to do this. So when you plug this here, so you see that this gamma of n plus 1 and this cancels out, and when you combine this one and this one, so this two things becomes in the denominator of this thing. So basically we are going to have our j sub n of x equals the sum as k goes from 0 to infinity of negative 1 to the k over its k factorial times gamma of n plus k plus 1 and times x over 2 to the n plus 2k. And hence we proved this here. And yeah, this is the solution to the Bessel's differential equation. So yeah, thank you so much for watching this video, guys. And if you have learned from here, so make sure to like and subscribe if you can. And yeah, stay tuned for the next video. And maybe I'm just going to continue making videos on Bessel function because I'm having a lot of fun in this. Yeah, and yeah, I think we should just leave here. And yeah, thank you so much for watching this video. Goodbye. Take care. Love you all.